Hi everyone, my name is Vincent, and this is a photo of me. In this series of videos, I'm going to explain Scikit-learn to you. Scikit-learn is the go-to library for machine learning with an amazing ecosystem of plugins. And in this series of videos, I will highlight some of the most important parts to understand if you're going to be working with this tool. What's important to note is that these videos that I'm about to show you originally appeared on Calm Code. This website features short videos about a topic in a series, so what I've done is I've concatenated the videos about Scikit-learn together for this free Codecamp video. That means that this long video is split up into different sections, and each section will highlight a different but relevant Scikit-learn topic. Now note that all the code for the videos that you're about to see is available on GitHub. You'll find a link in the show notes, and you can download each notebook yourself locally to run them, but you can also use a service like Google Colab as well. So let's talk about the topics that we will be discussing in this video. In the first section, we'll discuss some high-level topics involved with Scikit-learn. They are mainly there to help you appreciate how to construct machine learning pipelines, but the videos will also try to help explain to you why machine learning is still hard in practice. After all, machine learning tends to go beyond just optimizing a model. After that, we've got a segment where we will talk about pre-processing tools. You can use a Scikit-learn model, but the performance of the model really depends a lot on how the data is pre-processed. And understanding this pre-processing step tends to make your models a lot better. Next, if you want to judge a model, you'll also need to think about how to quantify its qualities. So in this section, we'll talk about the metrics that Scikit-learn offers, but also how to build custom metrics to judge your machine learning models on for your own specific use case. After that, we're going to discuss meta-estimators. The idea here is that while you can pre-process data as a step in your machine learning pipeline, you sometimes also want to apply post-processing. In order to properly explain this though, we will have to discuss these things called meta-estimators. Then finally, I would like to demonstrate a machine learning library that integrates with Scikit-learn that tries to make machine learning a little bit more human. The tool is called Human Learn, and full disclaimer, it's a tool that I made myself. The goal of this library is to show you how you might be able to benchmark the domain knowledge that's inside of your company before you resort to machine learning. Now, I hope that these topics indeed sound interesting to you, but let's now get started with understanding Scikit-learn. Scikit-learn is possibly the most used machine learning tool in the world. And in this series of videos, I would like to explain the general flow of how to use Scikit-learn when you want to make predictions. Now, for reasons that will become clear later, we are going to use a very specific version of Scikit-learn in this series of videos. In particular, we'll be using version 0.23.0, and if you're in a Jupyter notebook, you can use this command to make sure that you've got this specific version installed. It should also be said that this series of videos is different than some of the other series of videos on this website. In this series of videos, it is extra important that you watch all of the videos. Not just the first few, you actually need to watch all of the videos to get a proper understanding of how to use Scikit-learn appropriately. Also, the Scikit-learn ecosystem is vast, and it's impossible to do it justice in just a short series of videos. The goal of this series of videos is more to give you a bit of an overview on how in general you should think and work inside of Scikit-learn, but there will be other series of videos that will go more in depth in a certain aspect of Scikit-learn that I will not be able to do justice in just this series of videos. That said, let's dive in. The way Scikit-learn works is you start with some data, you then eventually give it to a model, the model will learn from it, and then you will be able to make predictions. That's the general flow. However, let's be a little bit specific. Just giving data to a model is a bit vague, so what do we mean by giving data to a model? Now, typically, if we have a data set that's useful for predictions, then we can split the data set up into two parts. And the common notation is to call one part of the data X and the other part of the data Y. Now typically, my data set X represents everything that I'm using to make a prediction. And my data set Y contains the prediction that I'm interested in making. The use case that we're going to deal with in a moment has to do with house price prediction. So you can imagine that this Y data set that contains the house prices, and X over here contains information about the house. Things like square feet, how big is the garden, that sort of thing. If you split your data up in this fashion, the next thing that you can do is you can pass that to your model. And then it's the model's job to learn the pattern such that we can predict y using x. This x and y notation comes from scientific articles, and because it's the notation that scikit-learn adheres to, it's also the notation that I will use in my videos. What we'll do next is go back to our notebook and get ourselves a dataset that scikit-learn provides that gives us our x and y. Given that we have scikit-learn installed, what I can do is I can say from sklearn datasets, I can type load, press autocomplete, and then I see a whole lot of datasets that are at my disposal. And these datasets are meant for benchmarking and educational purposes. And what I'll just go ahead and do is I'll load the Boston dataset. That's a dataset that contains house prices of Boston, I believe in the 70s. Now, if I call the load Boston dataset as is, it's going to give me a dictionary with lots of items in it. However, there's a parameter that we can set called return xy, and if we set that to true, then we get two arrays out. One array represents the house prices, and these house prices are in thousands of dollars, and these are all properties of the houses. One nice thing that I can do is I can type x, y equals, and then I've got my x and my y that I can go ahead and use inside of a scikit-learn model. So what we are about to do is make a model appear inside a scikit-learn. But just conceptually, it is nice to point out what a model does, actually. When you create a model, it hasn't seen any data yet. There has to be this moment where we declare that this model over here learns from data. And in scikit-learn, that means that there are two phases. There's phase 1, where we create the model, and then there's phase 2, where the model has to learn from the data. In scikit-learn, all models are just Python objects, and then this learning over here, in scikit-learn terminology, that is often called the .fit step. And during that fit step, we typically pass it the x as well as the y dataset. It's important to know that these are two separate phases that the model has to go through if we want it to be able to make predictions. But given that we've highlighted this overview, let's go back to the notebook and show you what the code might look like. So let's load up our first model. Scikit-learn comes with many, but one of my favorite ones is the k-nearest neighbor model. And you can find it in the neighbors submodule, and I will grab this k-neighbors regressor. Now, for the creation step, what I will do is I will have a variable called model, and that will point to this model object. Now, at the moment, there hasn't been a phase where the model was able to learn anything. So if I were now to call model.predict x, as in, hey, model, could you perhaps predict y using x? Then right now, I will get an error. And that's because the model has not been fitted yet. However, if I were now to say, hey, model, please fit yourself, x, y, now by calling this, k-neighbors will learn from the data as well as possible, such that if I now wanted to make a prediction, it is able to do so. And you can verify yourself that the number of predictions that we're making is equal to the number of rows in our x array. Now, I'll discuss later what this machine learning model does exactly, because you might wonder how the predictions get made. But one thing I would just briefly like to point out is that I can also use another model, say from scikit-learn linear model, I'm just going to import linear regression. But the beauty of scikit-learn is that even though this is a completely different machine learning model that internally works very differently, the API is still exactly the same. If I were now to replace this k-neighbors regressor with this linear regressor, then I can run all the cells, and sure, the predictions will be different because it's a different model. The internals work differently, but the API is exactly the same. It's still .fit, .predict. And it's this what makes scikit-learn very nice to use. You can stick to a general API and not have to worry too much about the internals. And that is very nice. So I'm back in a Jupyter notebook, and what I've got is my trusty k-nearest neighbor model, and I am fitting that model such that later on I can make predictions with it. And what I've got now is this array of predictions, but what I've also got is this array of original values. These were the true values, so to say. So one thing that I typically like to do is just make a scatter plot. I will show the predictions on the x-axis and the predicted values on the y-axis. And by looking at this, we get a bit of an impression of how well the model is doing. It's just a plot, but it does give me an impression that in general, it seems to pick up something of a signal and that there indeed is some form of correlation happening as well. When our model says the house price should be high, it seems to be high in reality as well. It's not perfect though, and it's a little bit noisy here. And there's a couple of reasons for why that may be, but let's now talk about how this k-neighbors regressor works. Let's consider a simpler version of the dataset. And the dataset contains square feet that a house has, as well as, let's say, the proximity to school. Let's say it's these two. And let's assume that if you have a big house and proximity to schools is relatively small, then these red dots indicate that these are indeed the expensive houses. And you can imagine maybe the cheaper houses being over here. Now, the way that a prediction is made when you're using a k-neighbors regressor is, let's say I want to make a prediction for this point right over here. Now, what the model will do is it will start looking for its nearest neighbors. Let's say we're looking for the nearest 5. I suppose that will be these. If I look at the distance from the point that I'm trying to predict to all the other points in this dataset, I think these might be the nearest neighbors. Now, the prediction for this data point will be the average of these 5 neighbors that we've found, and that is how a prediction is made. But here is where the tricky thing can happen. It might be that the proximity to a school here is in miles, and it might very well be the case that you might have 1 mile over here, 2 miles over here, and 3 over here, but these square feet that we have on this axis, well, that can be well in the thousands. So that means that the distance that will be used to find neighbors will be very different on this axis compared to this axis. Because this x-axis just features larger numbers, it also means that that axis will have a much bigger effect in our end predictions. And that might not be what we want. So this means we have to rethink what our model actually is. At the moment, this is our high-level overview of what a machine learning model is. Still data going into the model, and then we get a prediction eventually. But maybe we have to rethink what a model exactly is here. Because if I think about the example that we just saw, maybe before this dataset X goes into this model over here, maybe we would have to do some pre-processing first. We saw that the square footage can be in the thousands, and maybe school proximity can be in singletons, so there might be something to be said about applying pre-processing before it touches the model. So let's draw that. So here's the redrawn schematic. The idea is that we take our data set X, and before we give it to our k-nearest neighbor, we apply some sort of scaling, just to make sure that the effect that each column can have on the prediction is on a level playing field. And doing this will make this k-nearest neighbor predict rather differently. And when you think about it that way, maybe we need to redefine what we think a model is. Before, we said that it is this k-nearest neighbor that is the model, but maybe we should expand that idea. Maybe everything inside of this box is the model. If the pre-processing has a large effect on the model itself, then for all intents and purposes, we would like that to be part of our entire system. So that said, maybe it's more this pipeline that I've drawn over here that should be regarded as the model. And it just so happens that in scikit-learn, we have this notion of a pipeline, and this pipeline also has the API where we can call .fit on the entire pipeline, as well as .predict once it's trained. The reason why that is so nice is because this pre-processing step also has to learn from the data in order to properly scale and normalize. And by putting everything into a pipeline, we are able to just handle that automatically, such that we still have to interface with one object instead of many. So I hope this overview paints a clear picture of why we like to have a new definition of what a model is. And what I'll do now is I'll just implement this in the Jupyter Notebook. So let's first import the parts that we need. From scikit-learn, I will need to import from the pre-processing module something that can do scaling. And for that, I will just use this standard scalar object. Next, what I'll do is I will also import the pipeline object. And that allows me to chain processing steps after each other. So what I will do now, having imported these tools, is start a new pipeline object. It needs a list of tuples, and it's a pair of a name as well as a step. Do keep in mind that you have to pass the object over here, not the class. So it's important that you use these brackets. After we've done scaling, we would like to use our nearest neighbor. And this is the pipeline. What I can now do is just call pipe.fit x, y, and this entire pipeline will now train and fit itself. And what I can go ahead and do is I can replace the model that I had originally over here with the pipeline that's now also scaled, And when I run this, we should see a new graphic appear as well. So I don't know about you, but this does look a bit better because there's less noise. There is one other issue though that we've just introduced. So let's have a look at what's actually happening now, because we're cheating. I'm telling the pipeline to go ahead and predict using this dataset X. But note that that's the same dataset that we're using in the .fit moment. We are learning from the same data as we are judging on. And the k-nearest neighbor will do something now that's cheeky. Suppose that I want to make a prediction for a point that's, let's say, over here. What I will then do is I will grab the 5 nearest neighbors, and then I will make a prediction for this one point by taking the average. But we're not making a prediction like this in our scatter chart. The point that I'm trying to predict is a point that's in our original data set as well. So what we're actually doing now is we're saying, suppose I want to predict this point, what are the nearest 5 neighbors? And well, the nearest 5 neighbors would include these 4 points, as well as this original point. So that means that I'm literally using the data point that I'm trying to predict in order to figure out if I'm doing the prediction well. As far as judging whether or not a model is good, this chart over here is giving us a view that is too optimistic. And I can force it too. What I'll quickly do now is I'll just change the pipeline a little bit to emphasize what's currently going wrong. This k-neighbors regressor has a few settings. And in particular, we have this number of neighbors that we can set. So let's change this number from 5 to 1. And I will run every single step now again, just to show you what the effect is. If I only select one neighbor, then the chart falsely suggests that we're making a perfect prediction. But the model here is only able to do that because it's allowed to memorize the original data. The nearest neighbor here is the original data point. So this chart doesn't tell us anything about how it might predict points that are not in the original data set, and this is a big issue. We want our model to predict data that it's not seen before. And we cannot trust charts and statistics where the model is allowed to predict on the same data that it's trained on. And that brings us to 2 issues. The first issue is, how can we get a fair comparison going for ourselves? But perhaps another issue is, how do I go about picking an appropriate number of neighbors here? And when you consider thoughts like this, you might realize that we have to review our understanding of what a model is one more time. Currently, this is our belief of what a model is. We have this pipeline, and there can be multiple steps inside of it. But now we have another issue, because now we might have some settings for the k-nearest neighbor. I might want to try out the system where we have 1 neighbor or 2, all the way up until 10. And I would like to pick this number of neighbors setting such that my model makes the best predictions. And in order to figure out which predictions are the best, one thing that we can do is we can compare our prediction with the original label. But as we've seen in the previous video, we have to be really careful here. We don't want to judge the model on the same data set as we're learning from. And with that in mind, maybe we should do a trick with a data set just to keep the methodology clean. And here's the idea. I'm going to cut this data set up into, let's say, 3 different segments. And what I'm also going to do is I'm going to copy both data sets 3 times. And here's the idea. First, I'm going to say, well, let's give this the predict name, and let's do that over here. I'll set the predict name here in the second set, and I'll put predict down here in the third. And I'm going to declare the other parts for training. The first time around, this part of the data set is going to be used for training, and then given that trained model, I can use this portion of the data that's not been used for training to test how well my predictions are going. And in the next data copy, I'm going to repeat the exercise, but a different portion of the data is going to be used for prediction as well as training. And finally, the same thing happens here as well. The idea here being, I'm going to call .fit.predict here, but I'm fitting on the green part and I'm predicting on the red part. This prevents me from ever predicting on data that I've used during training, but it does allow me to judge in the predict section of my data how well my predictions are. And the idea essentially is, if I just repeat this, then maybe I'll have a pretty good metric of performance for when I had 1 neighbor selected, when I had 2 neighbors selected, and when I had 10 neighbors selected. However, in Scikit-learn, all of this is something that the pipeline will not handle for you. Instead, there's a different object. And the name of this object is a grid search CV object. The idea behind it is that you can give this grid search a pipeline, and you can also give it a grid, like this number of neighbors over here, and internally it will perform cross-validation, which is the procedure that I've explained here. And by performing this cross-validation, we have a methodology that is somewhat sound. And what I would argue here is that maybe this grid search object, maybe that is the model that we should be thinking about. And in scikit-learn, also this grid search has a .fit as well as a .predict method attached. So let's turn this pipeline into a proper grid search. The first thing I'll need to do is make sure that I have my grid search CV object imported, and you can import it from sklearn model selection. And the object that you're interested in is this grid search CV object. And given that we have this imported now, what I can do is I can start a new grid search object. To get started with it, I need to pass an estimator. And an estimator is something that has a .fit as well as a predict, and the pipeline that I've made earlier, this one over here, will do just fine. Next, what I gotta pass is a parameter grid. And this parameter grid is going to represent all the settings that we would like to go over in our pipeline. In particular, the one that we're interested in changing is this number of neighbors in this k-neighbors regressor. Now, to set the grid, we need to have the name of that parameter, and the easiest way to get there is to use the getParams method that is on every scikit-learn estimator, including this pipeline. And when you run this, you will see all the settings that you're able to tweak. In particular, you'll notice that there is this number of neighbors property that's on this model. And the name model that I have here corresponds with this name of this pipeline step here. And the number of neighbors that I have here corresponds with the number of neighbors that are a parameter in this object over here. For our intents and purposes though, the only thing I need to grab is this one, but know that you can grab more here if you would like to change more parameters. And what I'm going to do is I'm going to say, hey, you know what? These are all the values that I would like you to check. And I would really like this grid search to also do cross-validation. So let's set the cross-validation parameter to 3. And now this is my model. Oh, forgot a comma there. Now, as far as grid search goes, I would like to mention that what we're doing in this one over here is relatively basic. I will leave links to other video series where we're going more in depth, but the main thing that I want to give you as a high overview of what will you end up doing when you have a grid search like this, well, you are simply just going to call model.fitxy, just like every other estimator we've seen so far. Except in the grid search, what will happen is we will have all sorts of settings and cross-validation that's happening on our behalf, so we don't have to write that code ourselves. However, once this has trained, there is this very interesting property available called CV results. And note that this property ends with an underscore. The grid search will train, and for every cross-validation, for every setting, it's keeping track of a couple of numbers. And what I can do is I can just give that dictionary that we have as output there to a pandas data frame. And here what you see is all sorts of statistics. You see how long it took to fit the entire thing, and for every parameter that we have, and for every cross-validation split that we've made, we can see how well it did on a certain score. And we can also see which result was the best. And at this point in time, it seems like we've found that this might be the best setting, and that's interesting. And at this point in time, we can spend a little bit of time analyzing this generated data set to figure out why that might be. The main point I'm trying to make so far, though, is that with only a very small amount of code over here, we have a fairly mature pipeline, and we also have a proper set of Lego bricks to build machine learning systems. And if you'll be using scikit-learn a lot, this is the pattern that you are eventually going to be aiming for. We have a proper pipeline that we can go ahead and tweak quite easily. It's clear what steps are happening. The steps are reproducible as well. And as far as methodology goes, we can argue that we're doing a couple of things right because we're using this grid search object over here. So try to stick to this pattern whenever you're using scikit-learn. The system of fit-predict that scikit-learn offers and the way that it allows you to construct pipelines is something to appreciate. That said though, we could ask ourselves, have we now found a model that can go to production? Have we done our work? Are we now proper data scientists? And the answer is no. And I have to highlight why, and this is also the reason why it's very important that you watch all of the videos in this series. So far, we have been using the Scikit-learn API appropriately. Now, I use the word appropriately here in the sense that we've been using its building blocks in the right way. We click together a pipeline, we've been using a grid search, and so far I would argue these are all good things. As far as an approach to a data science project though, we could not have done it worse. And I would like to explain to you why. We've been using this load Boston dataset, but during the entire analysis we've not taken any time or even bothered to look what's actually inside of this dataset. Now, when I just run load Boston like so, you will notice that I get a dictionary. One of the things inside of this dictionary is this description tag. And what I can do is I can get a description of all the variables that are in the dataset. Now, if I want to get a nice output, I have to print what is returned to me here, so I'll do that. And what I can now do is I can have a little look at what we're actually dealing with. So first of all, you can kind of wonder, is 506 houses enough to give us a lot of confidence in our model? Maybe not. We can also ask ourselves the question, hey, from what year is this data? It might be that this data is really old and that the world has moved on in a way that this dataset doesn't really represent what's currently happening. That's also a valid concern. But it gets worse. We also never bothered to look at what attributes are actually in the dataset X that we're using to make a prediction. So we have things like crime in the neighborhood, we have things like how industrious is the area, but the one that I was really concerned with when I first looked at this is this one. Apparently this is a dataset where the proportion of blacks in your town is something that is actually being used to predict a house price. Now, I don't know about you, but I'm having a really hard time coming up with a use case for this dataset that is appropriate. Looking at this feature, it's clear to me that we have a potential for a racist algorithm, and that is a property I don't want to have in production. Now, there's a lot of things that can go wrong when we deploy a machine learning model, and we've discussed methodology, and these are fine topics. It's good to worry about that. But grid search is simply not enough. And what has been bothering me is that this dataset has been used for so long in so many different courses without even looking at the variables that are in here. Putting a model that has this feature in it is incredibly naive. And I think as a profession, it really helps if we just do better. This is also why Scikit-learn has now chosen to remove this dataset. Load Boston, after a few releases, will be gone. And this was the reason why I had to pin the version number of Scikit-learn in the beginning, mainly because the Load Boston dataset in a future release will no longer be available. Remember this chart that we made halfway in this video series? It contains our predicted values versus our true values, and this chart was generated because we were using the same dataset that we trained on as we evaluated on. And the danger here is that the chart suggested that our model was better, even though the model was effectively leaking information. If we had blindly trusted this model, then the risk is that this model might have gone to production with very high expectations, and the results clearly would not have been great. The only way to catch these sorts of things in practice is to remain skeptical. You should always feel free to distrust the model and to try to test every weakness that you can come up with. Only after a long period and lots of stress tests are you allowed to put a little bit of faith into the model that you have. And note that the same thing that happened in this chart also happened to us while we were doing the grid search. The grid search introduced a methodology, and we certainly have statistical concerns when it comes to a model. If it has poor predictive power, then it won't be very useful in practice. But we should maybe mention here that there is a danger in doing this grid search. It may give you the impression that you're doing the right thing. After all, numbers go up, and you might get optimistic about the quality of your model, and it's exactly this optimism that might be causing you to develop a blind spot. It's the time during which you make these optimistic charts, as well as when you see numbers go up in your grid search, that you forget to think about things like, hey, what's actually in my data? And I hope the Load Boston dataset, as we've seen in the previous video, makes it clear that you cannot just blindly put any data into a model. You actually have to spend some effort and try to understand what you have at hand. There are many things that can and have gone wrong in the application of machine learning models, and I would argue that it's also your responsibility to educate yourself to make sure that it doesn't happen to you. If the output of a machine learning model is your responsibility, then so is the data going in. So please use Scikit-learn and its amazing Lego brick-like features, but also understand that Scikit-learn typically
is the easy part of the profession. The hard part is understanding the story behind the dataset, and to understand what might go wrong when you put a model into production. And that means that it would be good to make sure that you're up to date on themes of ethics in algorithmic design, but also topics like feedback mechanisms, and to consider fallback scenarios for when things go wrong in production.
That concludes the Scikit-learn portion of this video. This would be a good time to grab a drink or have a quick break, and in the next portion we'll talk about pre-processing tools inside of Scikit-learn. Quite typically in Scikit-learn, you'll have your labels and you'll have your data that you want to use to make a prediction, and then both of these eventually will be passed to a model, and then you'll have something that is able to make a prediction. But the idea of what a model is can be extended here, because if you think about what happens, more often than not, it's a pretty good idea to first transform your data that you're using for the prediction, and the reason for doing that is because the model performance will just be a bit better by doing so. So what I figured might be a good idea was spend some videos explaining some of the more frequent transformers that people tend to use, and to also show that it's important to not forget about these transformers because they do really matter in your pipeline. So what I've done here is I've started the notebook, I've imported NumPy, Pandas, and Matplotlib, and I've imported this dataset called drawdata1. And it's a CSV file. It has a column X, a column Y, and a column Z. And Z has two values, either A and B. And the idea is that these are just some numeric numbers, and we're trying to predict this one column over here. And using Matplotlib, we can show what the dataset looks like. So we've got a group of data points over here, and another group of data points over here. And we should notice that there seems to be like a small group of outliers over here, as well as a small group of outliers over here. But another thing that you should be aware of is that the y-axis over here is on a completely different scale as the x-axis over here. And that can be something that's bothersome. The effect that these axes will have depends on your algorithm, but in general, you can imagine that algorithms are sensitive for this kind of thing. So a large chunk of your pre-processing in this case is going to revolve around scaling. We want to rescale this data such that there's still information in there, but it's just numerically a bit more stable because the x and y axes are just a little bit more in line with each other. And as you might be able to guess from the name, a standard way of doing this is using the standard scaler from Scikit-learn. And what it does is for each column, it is going to calculate the mean as well as the variance. The idea here being that if you have a data point x and you subtract the mean of x from it, and then you divide by the square root of the variance, well, then you're going to have something that revolves around 0. And this will also have a variance that's kept at bay. So what I'll now do is I'll just go ahead and use the standard scaler to rescale the dataset that you see here. To use a standard scaler, we first have to import it. And next what we have to do is we have to create a scalar object. But from here, we should be able to call fit_transform and give it our dataset x. And this will be our new transformed dataset. And what I'll just go ahead and do is I'll just copy this plot code over here and put that down here. This way I can just feed it the new values for x, and we can see what it looks like. So one thing you should notice at this point is that these axes numerically are much more similar. But it's not exactly perfect though. It seems that this spread is about 8 units, whereas the spread over here is more like 3.5. And we can also observe that there's nothing really happening with these outliers. So the standard scaler is doing things we like, but it does make you wonder, is there maybe another way of scaling this? To further demonstrate what might be a weakness of the standard scaler, I figured I would generate a dataset to make the point just a little bit more tangible. So what I've got here is just some data that has a couple of outliers on one end. And what I'm going to do now is I'm going to say, well, let's take that dataset, let's subtract from that the mean of the dataset, and let's then divide by the standard deviation. And whenever I run this, I have slightly different data because I'm simulating data, but as I'm running this over and over, you should notice a few things. And yes, for starters, definitely the numbers we have here on the x-axis, these are definitely scaled, so you could argue that that's a good thing. But the downside is we still have outliers. And depending on the algorithm that you're using, outliers will make life a little bit harder for you. So let's instead conceptually come up with a different way of normalizing, where these outliers are just a little bit less of a problem. So let's say that this is my original dataset. Now what I could do is I could calculate the mean value, which would probably be around here, and I could then say, oh, let's standardize around that. But let's calculate some other values instead. Let's ignore the mean for now. Instead, what I could do is I could calculate the quantiles. I could imagine, for example, that the 50th percent quantile is over here. And that means that 50% of all the data is on this side of the line, and 50% of the data is on that side of the line. I could imagine that maybe the 25th quantile is over here, and that means that 25% of all the data is on the left side, and 75% is on the right side. And I think that the 75th quantile will be somewhere over here, and let's say the 99th that might be over here. This is something that we could go ahead and calculate. And if I were now to think, hey, how can I project that onto something that's normalized? Well, I could have a number line down below, and I would have the number 50 halfway, the number 100 would be all the way to the right, the number 0 would be over here, I would have 25 over here and 75 over here. And I hope you can see that there's a mapping here. And notice when I scale it this way, that then in this scaled representation, the distance from the outlier to the 75th quantile is a lot smaller. And that means that by using quantiles, as opposed to means and standard deviations, we may be able to get a more robust pre-processing step if there's outliers in here. So let's use this idea as a pre-processing step and see what the effect is on our dataset. So from scikit-learn pre-processing, I can now import the quantile transformer. And what I'm going to go ahead and do is I'm going to replace the standard scaler with that quantile transformer. But before I run this, notice the axes, the numbers that are the minimum and the maximum, and also notice these outlier clusters. I'm now going to run this and show the effect. Now, there's a warning. Typically, scikit-learn likes to calculate 1,000 quantiles, and the dataset that we gave it doesn't have enough data for it, so what I'm just going to go ahead and do is turn that number of quantiles into 100. But notice that the minimum as well as the maximum on both axes are exactly equal to 0 and 1. And you might also recognize that the clusters that we saw earlier are still in the data, it's just that they have less of a profound effect. And the reason for that is because now we're using quantiles to transform and scale, as opposed to using the mean and standard deviation. In the previous video, we showed that when you take your X matrix and you pass it through a transformer, the quantile transformer, that you can get a very different output. And what I would like to show in this video is that when you take that output and then pass that to a model, that then the predictions are also going to be very different. So what I have done is I have made this plot output function. And what the function does, it allows you to pass through a transformer, and the function will then run all of this. It's going to train a model, a k-nearest neighbor model, and it will then also produce some predictions. And I just would like to show you what a profound effect this transformer can make in a predictive pipeline as well. So I'll first run it with a standard scaler. And what you can see here is the original data that we start out with, followed by the transformed data, and then we will see the predicted data, which is this final plot over here. And what you can see is that everything around this area over here would get predicted as the yellow class, and pretty much everything else will be predicted as the purple one. Let's now compare that to the quantile transformer. Because the transformed data is much less influenced by the outliers, you'll notice that the model is bound to think that there's just this dividing line between the two classes, and that's how we're gonna classify everything. And if I were to compare the predicted data plot, you'll really see a big difference. And in this particular case, I might argue, as far as numerical stability goes, the quantile transformer does have benefits, but it would still be a good idea to verify this with a grid search. But I hope that you can imagine that the quantile transformer, even with the grid search, is just going to be more stable in the long run, because these groups of outliers are not going to have as much of an effect anymore. Let's now have a look at a different dataset. In this case, I'm looking at drawndata2.csv. And this dataset is special in the sense that it's a dataset that represents a classification task that is not linearly separable. It's not possible for me to draw a single line such that on one side of the line I'll have purple points and on the other side of the line I'll have yellow points.
And this might make you think that a logistic regression is not going to be the right choice for this task. You may need to have a different algorithm here to get a good classifier. So let's see if that is accurate. So what you see right now is a pipeline that has a quantile transformer first as a pre-processing step, and then a logistic regression. And the best thing the logistic regression has been able to do is come up with this line as separated two classes. And this is obviously a bad classifier. These two groups should be the same color, and the line should not separate this way. But maybe we can fix this with pre-processing instead. If I consider the two axes that I have at my disposal here, then essentially what is happening is the logistic regression will get x1 and x2, and at the moment it can only use those two columns to come up with a separating line. But what if I generate x1 times x2 as another feature? That's something that the logistic regression might be able to use. And what about x1 to the power of 2 and x2 to the power of 2? What you could say is that we can limit ourselves to the linear features, but we can also just use those linear features to come up with non-linear features that our model might be able to use. So let's change the pipeline such that we add these features in as well, and then see what the effect is. From scikit-learn pre-processing, I can import the polynomial features and just start a new object over here. Now note that I'm not changing any of the input variables here, but one thing that's nice to point out is that I'm only calculating the interactions at the moment, and I'm only calculating this for a degree of 2, but I could increase this if I wanted to. But let's just see what the effect of just this is. Booyah. And if I were to scroll up now to compare, I would argue we have a near perfect classification. And granted, this is on the train set, so it's cheating a little bit. But what I do hope to have shown here is how much of an effect a single pre-processing step could have in your pipeline. The effects can actually be quite drastic. So far, we've been doing a lot of pre-processing on numeric data. But you can also imagine that we have data that's like this, where maybe we have classes, low, medium, high risk, and then it will be nice if we can do some pre-processing such that this text data becomes numeric data as well. The most common technique for that is the one-hot encoder. Now, what this encoder will do is it will be able to take in an array of text or categories and transform that out to something that is indeed numeric. Now, if you just run this as is, you're going to get a data structure that's known as a sparse matrix. There's a setting, though, that we can change such that the sparsity is false, and then we can actually see what is inside of it. Note that the first two rows are indicated as low, and we can see that indeed they share the same column. Then we see high over here, which is listed there, and then we see medium below, and that is listed there. So we can see a form of correspondence, and that is something that is indeed useful. And the most common use case for this is if this is, let's say, the class that you would like to predict, then this numeric representation, that is going to be the Y array that you're going to pass to scikit-learn, because this is something that scikit-learn can use to train numerically on. There is some behavior to be aware of, though, and this is not super relevant if you're generating labels, but it is relevant if you're using this one-hot encoder to encode information for the data that will predict the label. Let's say I grab the encoder now and I ask it to transform something, and what I'm asking it to transform is something that it's never seen before. So notice that I'm asking it to give me a label for 0, but 0 does not appear in this set, and that is the set where we did perform a fit on. So we might wonder, what's going to happen here? Well, we're going to get a big fat value error. So it's saying value error found unknown category 0. So essentially it is telling us you're not allowed to give me data that I've never seen before. We can change the setting for this though, because at the moment the handle unknown parameter is set to error, but we can change that such that it's set to ignore. And now if I run this, it's not going to give me an error, and what it's doing is it's saying, well, these are all zeros, or another way of saying that, 0 is neither low, high, or medium. So we can just go ahead and give it this 0 array back. Now, one thing to finally note about that is that this is a very useful setting if you're generating your X matrix, so to say, but you don't want to do that if you're generating your Y labels, because those are things that you want to have very strict control over. In this series of videos, I've shown you some of the pre-processing steps that are available, but A very convenient way for you to play around with more of them and to get a better understanding is to go to this website called drawdata.xyz. And full disclaimer, it's a website that I made, but it's a website that allows you to, quite literally, make a drawing of a little bit of data, and that way you can play with it from your Jupyter notebook, and playing with preprocessors is the best way to learn about them. Now what you can go ahead and do from here, once you've drawn your dataset that you're interested in, you can click this download CSV button to download this file locally. But what you can also do is you can copy the CSV to your clipboard. What you can then do is you can type pandas.read clipboard, and then this will be able to read from your clipboard. The only thing you have to do manually is you gotta set the separator to a comma, because I think the clipboard is typically reading in from Excel. But what I can now do is just run this, and lo and behold, the dataset that I was just drawing is now available to me here, and this is a really nice way to just get a little bit playful with scikit-learn preprocessing steps and pipelines. I hope that this series of videos has inspired you to check out these preprocessing steps a little bit more in depth, but mainly I would like you to remember that these preprocessing steps really do matter. They can have a profound effect on what your algorithm is going to end up doing.
And that concludes the pre-processing part of this video. Next, we will move on to metrics.
I was looking around for a fun dataset when I found one on Kaggle. It's a relatively well-known dataset about credit card fraud, and I figured it'd be a nice example to explain something about scikit-learn. Because Kaggle is giving me a dataset, and this dataset consists of a label that I would like to learn, as well as the data that I'll be using to predict that label. And typically you would start building your model, but you're not going to build one, typically you're going to make a few. So you're going to have model A all the way down to model Z. And these models might be the same type of model, but they're going to have different hyperparameters, and for all intents and purposes, they will be different models because of it. And all of these different models are going to have a different prediction. And what we would like to do is pick the best model. And in scikit-learn, you would use a grid search for this. And what the grid search will do is it will take all of these predictions and it will compare them against our original label using a metric. And it's important you get that metric right. Select the wrong metric and you're gonna pick the wrong model. So I figured it'd be useful to spend a few videos explaining how scikit-learn goes about this metric, because it is a really important part of your machine learning pipeline. So let's check the dataset before we talk about metrics. I downloaded the dataset into a CSV file that's on my downloads folder, and I'm reading it in with pandas. And the dataset is a little bit big, so I'm only reading in the first 80,000 rows. The dataset has a lot of columns, and most of them are anonymized. At the end of the data frame, we see a class, that's the thing we're interested in predicting accurately, and we see an amount. The idea behind this dataset is that we have all sorts of anonymized features, that's represented by column V1 all the way down to V28. But all of these features describe characteristics of a transaction. And we also know the amount that was in this transaction. Now, to get this data frame into scikit-learn, it helps to have it in NumPy, and that's what I've done below. X contains all the columns that have a V in it, and Y is the column over here, what I'd like to predict. And to emphasize what kind of data set this is, let's print some useful information. So let's print the shape. And let's also list the number of fraud cases. So this looks like data that's ready for scikit-learn, but we have to be aware of one phenomenon, and that is the fact that the number of fraud cases, it's about 200, and that is out of 80,000 cases. So it's safe to say that this data set is unbalanced. There are way more cases with fraud than without, and that is something to keep in mind. So keeping that in mind, let's start with a simple model. And I'll just use logistic regression for now. So first I'm going to import it. And then I'm going to say, hey, please fit on that data and make a prediction as well. Now when I run this, I get an error saying that the total number of iterations has been reached. And what's probably happening here is that because this dataset is so imbalanced, it's not converging within the number of iterations that it has. So what I'll do is I'll just set the maximum number of iterations to be higher. I think the number of iterations initially is 100, but let's set it to 1,000. Okay, so that works. What I'll now do is I'll take the sum over all of the predictions that I have. So this is by no means a perfect metric, but what I would like to observe now is if I'm overfitting on just the train set, then the model detects fewer cases than I actually have in my dataset. So without grid search, I can already tell that this model could be doing better. So let's add a setting that might allow us to move the algorithm in the direction that we're interested in. And for logistic regression, one convenient way of going about that is to say, hey, let's specify the class weight. Now, the class weight is a dictionary that allows me to specify how much weight to assign to each class. And in particular, the way that you should read it is that for class 0, that will be the non-fraud cases, then we assign a weight of 1. But for my class of 1, which would be the fraud cases, I'm saying, well, let's give that double the weight. The idea being that we're going to get more fraud cases selected. So let's run this and see what the effect is. And booyah, I'm able to find more fraud cases this way. So this is a pretty good place to start. I have a setting here that I would like to optimize, and that means that right now I can start worrying about the grid search and about the metrics. So now that this basic example works, let's get a grid search going so we can find the best value for this class weight. And I'll start with basic settings. Let's first import it. And next, let's define our grid search. I'll first need to pass it an estimator, and that's our logistic regression in this case. And let's also set the maximum number of iterations to 1,000. The next thing I have to do is I have to set the parameters. And I'm interested in changing this class weight. So now I have to give it a list of settings to loop over. And in particular, the settings have to be dictionaries like so. And let's use a list comprehension for that. So next, let's specify how many cross-validations we want to do. And I'll just say 4 for now. And I have a couple of cores on this machine, so I'll set the number of jobs to -1. And that way, this grid search can occur in parallel. My grid is now defined, and what I can do is I can tell my grid to go ahead and fit. And it's done training. So I'll start a new cell here, because this grid object, it has a CV results property now. And this contains all of the results from the cross-validation. And that's a dictionary with lots of values, but I can easily turn that into a data frame. So when I look at these results, I see the class weight appear, and I also see the scores. So for every cross-validation split, we see this score. And it's this score that grid search is using to pick the best model. But then we gotta wonder, how has it come up with this score? Because we didn't specify any metrics in our grid search, yet it is able to find this score right here. Look, there's no metrics. Now, where that score comes from is from the model. I've got a logistic regression right here. And what I can do is I can ask for the scoring method that is in there. So we see that there's a bound method called score. And if I use 2 question marks, then I can see the implementation of it. So this is the implementation, and I see a docstring. And if I look at the implementation, it says that from metrics, it's importing the accuracy score internally. So that means that this logistic regression, it has a score, and unless we specify otherwise, the score for logistic regression is just going to be accuracy. And when I look down below at this mean test score, then that makes sense. The model is predicting no fraud most of the time, so we're getting a really high accuracy there. But this is not the metric that I might be interested in though, so let's change that. So let's import some things from the scikit-learn metrics module. And in particular, I'll just import the precision score and the recall score. Now the way that these score functions work, and I'll take precision as a first example, is you can pass it the true values. Those are the values that it should predict. And you can give it the predicted values. So I'll just predict some. And so far so good. I can do the same thing with recall. Now, precision and recall both measure different things. What recall will tell me is it will tell me, did I get all the fraud cases? And precision is saying, given that I predict fraud, how accurate am I? And you can imagine in an extreme example, if I were to say, hey, let's predict that every single case is a fraud case, well then the recall score is going to be really high, and the precision score is going to be really low. In another extreme case, suppose I find one candidate that's a fraudulent candidate, but nobody else gets predicted as fraud, then I'll have a really high precision and a really low recall. And you can imagine that if you're going to optimize for either of these two,
you're going to get a substantially different algorithm. And in this case, the crux is, do we care more about false positives or false negatives? For now, I'll assume that we care a little bit more about precision. So what I will do is I will take these two metric functions and add them to the grid search. Now let's add precision and recall to the grid search. To add it to the grid search, we have to pass a scoring dictionary. And I can say, hey, I've got my precision score and I've got my recall score. There's one extra thing we have to do though, and that is if you want to use these functions inside of a grid search, then we have to pass that to the makeScore function first. We'll discuss later why they make this distinction. But by doing this, we now say, hey, let's add these metrics now as well. The one extra thing that I have to pass now as well is the refit. If I just tell Scikit-learn, hey, these are the extra scores that I want you to keep track of, Scikit-learn will do it. But if I want this grid search to select the best model based on one of these scores, then I have to explicitly mention which score it has to optimize over. So let's run this. And it just ran. And one of the effects that you now see is that we have the test precision that's now listed here, as well as the test recall score. One extra thing that we could add now is these are the test scores, which are useful, but sometimes it's also nice to see the train scores as well. So we can set a flag that we want to also get the train scores in our cross-validation results. And if we now scroll all the way to the back, we should at some point see, yes, scores for the train set as well. Since the grid search is now pretty well set up, it will be good to do a proper run. So I will change two things. For starters, I'm just going to increase the number of cross-validations. By having more cross-validations, this will take longer to run, but we should have more accurate metrics coming out. Next, what I'll do is I will replace this range 4 with a NumPy linear space. And that allows me to say, hey, let's start at 1, let's end at 20, and let's have 30 steps in between. This should give me a higher resolution on the effect of this class weight. And again, by setting this value v higher, I'm telling the algorithm to focus on the fraud cases. So I will now run this, and when it's done running, I'll show some charts that summarize this. So it is now done running, and I've made a few charts. This is the first one. It shows the test results. We have the weight on this axis, that's the class weight, and we see the two scores on the y-axis. And if you want to have a really good precision, you have to be on this end of the spectrum. And if you want to have a really good recall, you have to be on this end of the spectrum. And note that if you want to have a balance between the two, that you're somewhere in the middle. So this is interesting, but you might wonder, what do the scores from the train sets tell us? And again, we have our class weight here, and our scores, but we get a completely different picture. So it's a good reminder that cross-validating results is a good idea. Because I've got two metrics now, Scikit-learn is able to optimize either of them. So at the moment, I'm able to either optimize for precision, which is going to give me the model over here with very, very high precision and very low recall, or I can say, hey, pick the model with the best recall, and then I have the opposite problem. Maybe instead I want to be here in the middle. And there are two ways of going about that. One might be to go for another metric that's inside of Scikit-learn. In this particular case, the F1 score is something that you might be interested in, because the F1 score represents a balance between precision and recall. But it might be more interesting instead to make our own. Scikit-learn does not support every single metric out there, so it is good to be able to write your own sometimes. And in this case, I think it might be cool to have one that selects the minimum out of the recall and precision score. If I select the best model based on this metric, then I will have a model that balances the two. So let's go and implement this. Now you might remember that the precision score function that we had, that's the function that we're using over here. But the signature of that function was that we said, hey, there's these true labels going in, and there are these predicted labels going in, and the output of this function was a number. So let's use that as a template to create our own. And I will call this the min recall precision. And if I want to calculate the minimum between precision and recall, I'll first calculate the recall. Next, I'll calculate the precision. And then I'll return the minimum of the two. Let's now add this to our grid search. I'll just call that the minimum of both. And again, I gotta pass that to the makeScorer. And let's now also say that the grid search has to refit on it. Let's now run this. It's done running now. And let's have another look at the charts. I updated them while the grid search was running.
So one thing that's interesting is it does seem that the grid search would now pick a model that's around this region over here. I can't exactly see where, but it makes sense. It's close to where the two are balanced. So that's interesting. But you might wonder, well, the green line, that green line, that's always lower than either of the two. And you might wonder, well, why is that? I'll leave it as a small exercise for yourself to figure out why, and you can check the appendix for the answer. In the previous video, we've made our own metric here, and then we used it in the grid search over here. But before we were able to use it, we first had to pass it to this makeScorer function. And it wasn't just our own function, we also did this for the precision and the recall as well. So what's up with that? So to show what is happening there, let's make a scorer using our min precision recall function, and then let's just have a look at the implementation. So the makeScorer function apparently takes the min recall precision function that we had, so that's this one, and it takes that function and then turns it into a predict scorer object. And it has a signature. In goes an estimator, x, y true, and some form of sample weight. So one way of looking at this is to say, well, we start with a metric function that accepts y true, the true labels, and y predicted, the predicted labels. And what makeScorer is doing is it's turning that into something else, some other callable object, where I can pass it the estimator, my x dataset, my entire y labels, and a sample weight as well. And this is what the makeScorer function does. The idea behind it is that sometimes you would like to use the function this way. If you're in a notebook and you just want to quickly use a metric, then calling that directly can be useful. But it would be a shame if you had to rewrite that function such that the grid search would be able to use it. Because the grid search likes to have something callable where you also have access to the estimator. Now, what I just quickly want to do is rewrite this function over here such that I no longer need makeScorer, just to demonstrate that this is indeed the case. And we'll do that using this signature over here. So I've copied the signature. This is now the input. And let's now fill in this function. Well, what I can do is I can first calculate the predicted y values from this estimator that is being passed in. So that means I can just say est.predict, and now I should no longer need this makeScorer. So let's run this. And it ran. And let's now just check if we get the same chart. Excellent. When you're looking at this min recall precision function, then there's probably a lot of parts that you recognize. For example, the estimator that we have here, that is going to be a logistic regression like we've defined here, with the correct settings for the class weight. And you can also imagine that we have this x here, and this y true, and that these will be the train or test set labels and datasets. But you might wonder, well, what's up with this sample weight over here? And sample weight, well, that's an extra feature that can be passed along. Certain machine learning models allow you to say, well, this row is more important than this other row. That's different than the class weight. The class weight that we have over here that says, hey, this class should get more attention. But the sample weight allows us to pass data that says this row is more important than that row. And in the case that we're dealing with fraud, where we have rows that resemble financial transactions, you could maybe say that maybe the transaction amount, maybe that's a valid setting. The really big transactions that have millions of dollars in it, well, sure, if there's fraud there, that's much more important to catch than if it's only about a single dollar. So one thing that I could do is I could rewrite this entire function to take that sample weight into account. One thing that I would need to do though, is I would also need to give a sample weight. And that's something I have to do over here. So let's say I'll do that. And what I can do here is I can say, hey, take that original data frame and take the amount column. That is the amount of the financial transaction. And just for numerical stability, what you can do is you can also maybe not take the exact amount, but the logarithm of it. This way, if you have really big transactions, then you prevent that we're overfitting on it. And what I'm going to do now is I'm just going to run this, and I'll leave this the way it is. I'm not changing this. If I have a principled way of taking that sample weight and translating that to a metric I want to optimize, then that is definitely something I can now do here, which is good. That's a benefit. That gives me flexibility. But I don't have the financial expertise to come up with a good rule now. So what I just want to briefly show is if we actually do this, what is the effect? Because even though we're not changing the metric, adding this effect will change the algorithm. So I'll run this now and show you the summary charts to see what changed. So just for reference, this is the original chart, and this is where the balancing point is between precision and recall. And let's now see how this compares. So the dashed line is where the balance was before, and the dotted line is where the balance is now. So adding sample weight will definitely influence the algorithm here, but it's good to know that we could also use this sample weight for our metric if we wanted to. So let's consider a new approach to this problem. We could consider that perhaps fraud is like an outlier. It's a rare event, but it's also something out of the ordinary. So one could wonder, sure, we can have a classifier go in there and predict whether or not something is fraud, but if we just have an outlier detection algorithm, might that not correlate with fraud? So what I would now like to do is replace the logistic regression with an outlier detector, and then adapt these metrics such that we can check if this is the case. So let's first write a little bit of code that can handle outlier detection. I'll just start by importing the isolation forest algorithm. And because it's an outlier detection algorithm, when I call .fit, it doesn't need a label, it just needs the dataset. I can still use it to make predictions though. So let's just run this. When I look at this output, it seems like everything here is a 1, as if it's always predicting fraud. But that's not the case. To show that, I'll just quickly import a counter object, and I'll just count this, how often a 1 occurs and how often another number occurs. And that's a thing. Scikit-learn assumes that a 1 represents not an outlier, and -1 that does represent an outlier. So if I want to translate these outlier detections, what I gotta do is I gotta say, well, if these predictions are equal to -1, then I want to have a 1, because that indicates a label for fraud, and 0 otherwise. Now with that observation done, let's just briefly go back here and look at our metrics, because a lot of stuff now will break. These recall and precision scores, they expect 0 or 1 values at the moment, not -1. So if I were to put an isolation forest here, the metrics would break. That is, unless I write my own variant over here. So I'll just quickly go ahead and do that. And there we are. I have made 2 functions over here that don't need the make scorer like we saw before. And by doing it this way, these predictions are now turned from outlier predictions into fraud label predictions. What I've now also changed is I have removed the logistic regression here and put in the isolation forest. And I have now also put in the contamination factor here as the hyperparameter that I want to tune. Again, I'll not go into the details on what that means, but we could say it's something I want to optimize. Finally, the 2 functions I have here, again, are being put into the scoring methods down here below. And here's the small amazing thing about this. Notice again that this isolation forest, when you train an isolation forest, you call it via fit, and then you pass it an X matrix without Y labels per se. But because we are passing in Y labels below here anyway, we are able to use them here in our own custom metrics. And that is something really flexible. That means that we can pass it, because that allows us to use outlier detection algorithms as if they were classifiers. So what I'll now just quickly do is run this and then make a similar chart like what we had before. So here's the similar chart. On the x-axis, again, we have our hyperparameter, and on the y-axis, we have our scores. And when looking at this, it does seem that even though the outlier detection algorithm is able to detect some things, it's not able to detect as well as the logistic regression that we had before. That said, this can still be a useful feature to have in your pipeline, but that is outside the scope of these series of videos. What is amazing here is that we were able to use metrics to quickly judge if an outlier model would be useful in this classification problem. In this series of videos, I hope to have been able to show you how you can use metrics in your scikit-learn pipelines, and that it actually offers a very flexible API. That said, I do think it's fair to point out that you don't always have to make your own metrics. Very often, the metrics that scikit-learn has will be relevant to your project too. You can have a scroll around. There's metrics for classification, but also for regression, and it's definitely worth to spend some time here on the documentation page. Before wrapping up though, I do want to point out one small danger with the current approach.
The way that we model things is by taking our data frame, passing it through a grid search to get our model, while also checking the metrics. And in terms of methodology, this is a fair approach. But there is one big danger, and that's especially true in the case of fraud. Do we really trust these labels? Especially in the case of fraud, it may be safe to assume that we don't have a complete picture of all the fraud cases. It's a cat and mouse game. So when I see a label for fraud, I think I can assume that that's accurate, but when there's no fraud, that might just be fraud that's undetected. And if we think a step further, probably the labels that I have, those are the labels of the easy cases. Those were the cases that got caught. And if we then train a model that optimizes for the easier cases, then we have to be honest, we might have a model that has a blind spot for the harder to detect fraud cases. So I must stress, it is really important that we keep track of our metrics and that we take that very serious because it has a huge impact on how we pick the model. But typically it is not enough. We still need to concern ourselves with the quality of these labels. Because if the labels are wrong, then so is your metric. In the previous video, we were using the makeScorer function to take our custom metric and to turn that into something that the grid search was able to use. And before delving in depth in what the makeScorer function does exactly, I figured it'd be good to point out that when it comes to customization, there's a couple of settings that you can still add. Not every metric will have the rule where greater is better. If you take mean squared error, for example, in that case, greater will be worse. So that is something you want to specify. Otherwise, the grid search might pick the wrong model. And there's also metrics that depend on having a probability measure being there as opposed to just a class. And if you need the probability measure for your metric, that's also something you got to specify. So for example, let's say I take this min recall precision function, and if greater was worse for this metric, you could specify greater is better is false. And then you would pass this in your grid search. Now note that this is of course a bit of a detail, but there will be moments when you need it, so I figured it'd be good to at least mention it. Let's now move on to a relatively fancy feature of scikit-learn, the ability to work with meta models. Usually in scikit-learn, what you'll do is you'll make a pipeline, and that pipeline will have pre-processing tools, maybe some featureizers, and after that you'll have a machine learning model. And the idea is that this pipeline is just a very convenient way to connect everything here. However, if you think about what you might want to have happen inside of a pipeline, then there might be some steps you would like to have after you've made your model. Maybe there's some post-processing you would like to do. The way that the scikit-learn pipeline works, however, is that you're able to have many featureizers and pre-processing tools chained together, but at the end, it stops with this model. The thing that can do fit predict, that should be the final thing in your pipeline. So that might make you wonder, how can we go about some of these extra steps and post-processing tools? We might have things that we would like to grid search, so it will be nice if there's a trick up our sleeves that allows us to still have access to these sorts of techniques in our scikit-learn pipeline over here. Now, it's a bit of an advanced trick, but the way to go about this is to think about meta estimators. Scikit-learn has a few of them, but there's a lot of them implemented in other tools like Scikit-Lego. Full disclosure, this is a tool that I made. But the idea is to have an estimator that can take this model and add extra behavior to it. It's a powerful modeling technique. And so in this series of videos, what I would like to do is highlight a few of these meta estimators and show you how you can use them to make your modeling pipelines a bit more expressive. Scikit-learn has a classifier that's known as the voting classifier, and it's an example of a meta estimator. To help explain what it does though, let's consider this classification task. It's definitely an artificial dataset. I'm using the make classification method to generate it. But what you can see here is that I've got these blobs of yellow points as well as purple points, and what you can see is that there are some purple points around here where there's mainly yellow points, and vice versa. There's also a few yellow points around here. Now there are two kinds of models, I suppose, that you could make here. If we were to say train a logistic regression on this dataset, then effectively what the logistic regression would do is it would pick the direction where it can make the most difference and then create one separating line. In this case, it probably will have a separating line somewhere over here, and it will say that everything on this end of the line is supposed to be the yellow class, and everything on this side of the line is supposed to be the purple one. A different algorithm, nearest neighbor, would do something slightly different. Whenever it needs to predict a point, let's say a point over here, it would look at all the neighbors, let's say the nearest 5, and then make a prediction. And that would mean that in this region over here, it might predict a purple point. And where the logistic regression is a little bit too general, as in it's splitting up everything here on the left and the right, you can imagine that the nearest neighbor is maybe too specific at times. And you might want to have a way to balance these two things out. And being able to balance these two, that is something that the voting classifier can do. The idea behind the voting classifier is that you can give it a list of estimators, and you can also give it a weight for each estimator. And that might allow you to say, well, I want this estimator to be weighted twice as heavily as this one. The nice thing about this is that this weight over here is something that you can use inside of your grid search. And that's really nice, because that means you don't manually have to specify these weights. You can have the grid search determine the best way to balance different models for your dataset. And here's an example of how the voting classifier works on this dataset. I've got my voting classifier over here that I've imported beforehand, and then I kind of submit something that resembles a pipeline. It's a list of tuples with the name that I associate with an estimator, and then the estimator itself. Note that the first classifier going in here is this logistic regression, and the second classifier over here is this k-neighbors classifier. But what I'm able to specify is I'm able to say, well, these are the weights I would like to associate with both models, and I would like you to do soft voting. And soft voting over here effectively means that we are averaging the predict proba values. Now, to show the effect of this, I've created a couple of charts. This chart over here shows the original data, and this chart over here shows the proba predictions of the first model, this one. And you can see we get the behavior that we expect. There's a line that's separating everything, and you're either on the left-hand or right-hand side of it. This chart represents the predictions from the k-neighbors classifier. And you can definitely see that it's zooming in on a couple of areas. We see darker colors appear in the yellow region, and we also see lighter colors appear in the dark purple region. And what you can see in this third chart are the predictions from this voting classifier, and you can see that we basically smooth the predictions of these two models. What I can do is I can say, well, let's give a somewhat higher weight to the k-nearest neighbor model. And by doing that, you can see that these two charts are now definitely more similar, but I can also give a higher weight to the logistic regression classifier as well. So there's two things to observe here. But first of all, there's merits to having such a voting classifier. You can combine different models that work different ways this way, which is nice. But moreover, the main thing that's happening here code-wise is that we have an estimator here that takes as input other scikit-learn estimators. This voting classifier is adding behavior to both of these models, and that can be a powerful modeling strategy. Note that if we put this voting classifier inside of a pipeline, that this is still the final model at the end of it, but we are able to add behavior because models can be used as input here. And this way of thinking about models gives us a lot of flexibility and expressiveness. Let's now say that we have a slightly different data set. Again, it's an artificial one made with the makeBlobs function in scikit-learn, but given that we have a data set like this, let's now talk about a different consideration for models. Let's say that we have a logistic regression that we'd like to fit on this data set. You might get a separating line that's somewhere over here, let's say. The way that this separating line works, if I were to draw it out on this axis over here, if I were to draw what the probability is that my predicted value is equal to 1, which I'm associating with these yellow points, then the predicted curve would look something like this. Now, what's happening here is we have a threshold around where the probability is larger or lower than 0.5 when we actually say to which class a point belongs to. You could wonder though, what if we just move that threshold just slightly? Maybe move it somewhere over here, maybe at 0.7. If we were to do that, then this classification line would move upwards. It would move over here. That's the new one, and that's the old one. Now, the consequence of doing this is that your model might become less accurate overall, but whenever we do predict that it's going to be a yellow point using this new line, we're probably more sure of it. In this region over here, there's some purple points and there's some yellow points. In this region over here, there's still a couple of purple points left, but it's less. So by tuning this threshold over here, we might have a nice knob to turn to exchange precision and recall in our model. And the ability to do this is provided by the thresholder meta model that you can find in the Scikit Lego package. The way that it works is similar to the voting classifier. We have a meta model over here, and as input it accepts an estimator. In this case, logistic regression. Thresholder accepts any scikit-learn model, but it only works in binary classification cases. What you're then able to do is you can set this threshold value over here, which again is something that you can put inside of a scikit-learn grid search. And here's the effect. You can see that if we set a very low threshold, that maybe the optimal line that we would have had over here kind of moves down a bit over here. This setting, I assume, will be great for recall, but bad for precision. And if we move the threshold to the other direction, over here, then we might have something that's very high precision, but very low recall. What I've got here is an example of how you can maybe use this inside of a grid search. I have my modeling pipeline over here. Inside of that modeling pipeline, I've got my one model, and this model has this threshold parameter. I can refer to that using model underscore underscore in my parameter grid here, which I'm using in my grid search. And what I'm doing is I'm just looping over all sorts of values of this threshold, and I'm keeping track of the precision, the recall, as well as the accuracy. And if we scroll down to the results of this grid search, we see some interesting things. The blue line over here represents the precision, and if we look at the threshold value, then indeed it seems that the higher the threshold, the more picky we are, and then also the better the precision is. As expected, this does come at the cost of this recall over here, which is the orange line, and we can definitely see it plummet whenever we have a high threshold value. Now, keep in mind that we're doing this on the test sets. We're not reporting train numbers here. Something that's interesting is that for this particular data set, it seems that as long as we remain, let's say, in this range of thresholds, the accuracy doesn't really change too much, but the precision and recall curves do. So that means that you don't have to give up your accuracy to get a bit of a boost in either precision or recall. And the nice thing about this threshold is that it's something that's easy to interpret, and at the same time, it's also a nice example of what I would call post-processing. In order to tune the threshold, I need to have the model ready. And it's this sort of post-processing steps that are probably best implemented as a meta model, as a model that accepts another model as input. What I've got here is a somewhat large pipeline that is predicting the weight of a chicken over time. It's being applied to a data set that has a diet column that says something about what the chicken's eating. Different chickens have different foodstuffs, and also time. The idea is that chickens gain weight over time, but they might gain more or less depending on the diet that they have. The way that I'm going about that is I am selecting the diet column and I am one-hot encoding that. Next, what I'm doing is I'm taking the time column and I'm just passing that through a standard scaler. Schematically, what is happening is whenever I get my new data set, it is going into this pipeline that has a feature union, which is splitting up the features into two buckets, the time feature and the diet feature. The time feature gets scaled, the diet one gets encoded, and then this becomes the data set that I can use for my machine learning. And it's this data set that is being used down below here for my linear regression. And here's what the predictions look like. For every diet, you see a new prediction line. Now, the downside of the way that we've encoded our data is that this linear regression sees the one-hot encoded variable for these diets, and the only way that it can deal with it is to see it as a constant shift. And if we think about the possible effect that a diet could have, then I hope that you might agree that we're not really modeling it the right way here. The effect of the diet might be something else than adding a mere constant. So then the question is, can we maybe reuse this diet in a different way? Maybe instead of adding a feature that is one-hot encoded for every diet, can't we maybe group per this diet and then train a different model for each? You would have model 1 for diet 1, model 2 for diet 2, etc. And then maybe what we can do is we can say, well, whenever there's a new data set X coming into this model, then what needs to happen is this internal grouping needs to figure out what diet this new data belongs to, and then make a prediction using the appropriate model. This behavior can also be implemented as a meta model, and Scikit Lego has an implementation of exactly this. And here's an implementation and the effect. In this case, we have a data frame that's going into this model over here. So that means that I can use the column name here to describe the group. But if it was a NumPy-like data structure, then you can also refer to the column indices over here. You'll note that when we do this, the effect of this diet isn't simply a constant. Instead, it's training a different linear regression. Each of these lines has their own intercept and their own slope. And I hope that you can imagine that making models this way can be reasonable. The main risk that you have to keep in mind is that it is possible that maybe one of these groups has way more data than another one of these groups. So that is something to keep in mind if you're interested in doing something like this. Let's now consider a time series task. There's a basic one over here. And one of the properties of this time series is that it's also changing over time. There's a seasonal pattern in here for sure, but the shape of this seasonal effect is definitely getting amplified as time goes on. So let's say you want to maybe model this. One way of modeling this is that we can say, well, let's have a look at every month in the year, and let's try to calculate the mean of every month, and then that can be our model. And what we can do is we can use the grouped predictor for that, as well as a dummy regressor. And if we were to then calculate the mean for every month, the prediction would look something like this. Again, note that we're using the dummy regressor from Scikit-learn here, and the grouped predictor that we saw in a previous video. When you have a look at these predictions though, you'll notice that something is definitely off. It seems that we're really good at predicting this middle year, but we're undershooting in the more recent years and we're overshooting in the far past. So that means that we have to wonder, well, what can we maybe do here to make this just a little bit better? And it's pretty good to observe that this is something reasonably general. In this particular case, I'm definitely looking at a time series, but it's not unreasonable to consider that the world is a moving target. No matter what you're trying to predict, there's something to be said to maybe focus in on the more recent data, and maybe to forget the data that's in the past. Now, the interesting thing is that Scikit-learn actually provides a small mechanism to deal with this. Not every model allows for this, but some models do. The dummy regressor is one of these models, though. And what we're interested in is a parameter that's tucked away in this fit method. If you look at the signature, you'll notice that the fit method has this simple weight parameter. It's a parameter that's set to none in most cases, but what you can do with it is you can say, well, how much do I weigh my data points? Let's say that this is my big input X and my array Y that I would like to predict, then I can have another array of sample weights. And what that allows me to do is it allows me to say, well, this data point over here, that's worth 0.1, this one is worth 0.2, and maybe this data point is worth 10. The idea behind these weights is that you can say that maybe this data point is way more important to predict than maybe this one or this one. And if you can specify this for every row in your data set, then this gives you an option to customize. Now, for our purposes, it will be nice to have a meta model that can automatically put values for these sample weights into whatever we're trying to predict. And in particular, something that's general is that we might say, you know what? Let's just do some exponential smoothing. If we assume that this data set here is sorted such that everything on this end is the most recent data and everything on this end is the old data, then maybe we can say that there's a decay parameter that says that everything that's happening here is super important, but as we move to the past, it gets less and less important. Now, this idea of adding a decay, that is a meta model that's also made available by Scikit Lego. And here's the implementation. And you gotta pay attention, because we're actually using two meta models here. We're starting out with our good old dummy regressor, but then we say, well, we want to add decay to it. What we're doing is we're saying, well, the more recent data points matter more than the old ones. Note that if you want to do this, your dataset does need to be sorted beforehand. Next, what I'm doing is I'm saying, okay, take that model, but now I want you to calculate the mean not on the entire dataset, but per month. And what's nice about this example is that we can demonstrate that we start with a very basic model, but by adding this meta behavior to it, we are quite expressive in what sort of model we would like to end up with. And we can see the effect over here as well. The orange line over here is what we would get if we didn't do any decay. And what you can see here is this green line, which fits the more recent data very well, but it doesn't really fit the old data as much. It doesn't really pay attention to that. And that's because we're adding a decay that's saying, well, ignore the faraway history and focus on the more recent events. One thing to keep in mind here is that by applying this trick, you will get this awkward situation where it is possible that your training data has way worse performance than your testing data. And that is because you're probably testing towards the future, and it's the future that we're actually paying more attention to in our model. So don't be too surprised if that's something that you see. But the main thing that I hope that you recognize here is that it's very nice to be able to take models that we already know and understand and just add small interpretable behaviors to it. It's that gives us the opportunity to customize a model to the use case that we're interested in. And not only will that make our models more accurate, but it also makes them just slightly more interpretable, which is always a good thing. In this final segment, we will talk about a tool called Human Learn. And the whole goal of this segment is to showcase that you don't always need machine learning. Back when data science was really just starting out, it wasn't really common to use machine learning algorithms. Instead, what was more common is you would start with a dataset, and then you would get a domain expert to come up with some business rules, and this would give you a system that could automatically assign labels to new data that came in. These days, though, it's a little bit more common to not write your own rules, but instead to have a machine learning algorithm figure them out. You would collect data as well as labels, and then it will be the job of the machine learning algorithm to figure out what the appropriate rules are. The question is, though, in this transition from a rule-based system to a machine learning model, have we maybe lost something along the way? And there's a couple of issues if you think about it. For starters, machine learning isn't perfect. It might be that the machine learning model is very accurate, but that it has behavior that we aren't necessarily proud of. Think of themes like fairness. And it might also be a little bit ineffective. Odds are that if you're starting out with data science and you've got a use case, that there's also a domain expert around who can pretty much tell you what rules already should matter. If nothing else, it would be nice if we can construct rule-based systems in such a way that we can easily benchmark it against machine learning models. So that got me thinking. Maybe we need to have a tool that makes it easier to write these rule-based systems. And that is why I started this new open source project called Human Learn. The goal of the project is to offer scikit-learn compatible tools that make it easier to construct and benchmark these rule-based systems. It is made in such a way that it's also easy for you to combine these rules into machine learning models as well. And in this series of videos, I would like to highlight some of the main tools of the package and how you can get it working in your daily flow. What I've got here is a Jupyter notebook, and one thing to observe is that at the top I have this pip install human learn command. And it's this command that makes this ulearn package available to me. What I'm doing in this notebook so far is somewhat basic. The main thing is I'm loading in this load Titanic function, and that allows me to load in this dataset about the Titanic disaster. The goal of the dataset is to predict whether or not a passenger survived. So we have a column here that we would like to predict. That's binary. You survived or you didn't. And there's a couple of things that we have at our disposal in order to predict that. We have the passenger class, we've got the name, gender, age. And what we can do is we can take all of this data and put it into a machine learning model and look for a prediction. However, if I were to come up with a simple domain rule that might also go ahead and work, then I could argue that perhaps I can also just have a look at this column here that tells me how much somebody paid. Something's telling me that the people who paid more for a ticket are probably also the ones who were perhaps more protected. Odds are that they were on the upper decks, and I can definitely imagine that they had better access to lifeboats than everyone else on the ship. So that means that I could already come up with a rule-based system. I could say, hey, let's just have a threshold on this fare, and everyone above the threshold survived and everyone below the threshold didn't. Probably the easiest way to implement this logic in Python is to write it down as a function, which is what I've done here. I'm assuming that a data frame goes in as the first argument, and then I have this threshold parameter, and effectively all the logic of predicting is happening in here. If you paid more than the threshold, then I'm assuming that you survived, and I'm returning a NumPy array. And what I could do is I could just say, hey, let's apply that fare-based function to my input data x that I've defined here. And I will get all sorts of predictions here. The issue with this is that this is a function.
it is not something that scikit-learn is able to accept as a classifier. And that means that I cannot use it in a grid search or a pipeline, and that's a bummer because I would really like to be able to grid search this threshold hyperparameter over here. Lucky for us though, there's a tool inside of human-learn that addresses this. The tool that we want to use now is called a function classifier, and I'm importing it here. What the function classifier will do is two things. It will take a function that you've written that outputs a prediction, and it will turn it into a scikit-learn compatible classifier. The second thing that it will then do is it will also make sure that any arguments that you've defined here when creating the function classifier that overlap with the arguments in the function itself, that those arguments can be grid searched, so to say. And to show you how it works, what I've done here is I've created a somewhat simple grid search. I'm doing two cross-validations, and I have a parameter grid here over the threshold. Effectively, I'm looping over lots of values between 0 and 100. And what I'm doing is I'm keeping track of the accuracy, the precision, and the recall. And what this grid search will do is it will pick the best hyperparameter based on the accuracy. When I call .fit over here, this system will run, and then I can inspect the grid search results. The grid search just ran, and I'm taking the results from it, turning it into a data frame, and then making a chart. What you see on the x-axis over here is the threshold value that we set on the fair column, and then you see three lines. The blue line is the orange line is the precision, and the green line stands for the recall. One thing that we can see is that when we increase the threshold, the precision goes up. That's the orange line. And this suggests that the rule that we started with isn't half bad. People who paid more for the ticket are probably more wealthy and are therefore perhaps more likely to get to a lifeboat quicker. Now, as a model, this isn't necessarily perfect. The recall that we have down below here decreases the higher we set the threshold. And that's also because there's less and less people that paid a certain amount for it. But all in all, this is already kind of nice because it allows us to test if machine learning models can make better or worse decisions than domain experts. And quantifying that can be nice. A final thing to mention about this is how general this is. We can come up with any Python function that we like here that has any logic that can cause a prediction. And then any argument that we have in the function can be used as a hyperparameter inside of a grid search. And this, in practice, can be very, very powerful. The function classifier is meant to be very customizable. That means that you can do more than just come up with a system that can make predictions. You can also use it to add behaviors to existing models. For example, let's say that I already have a classifier and that I also have an outlier detection system. Something that might be really sensible is that you first check for a new data point whether or not it is an outlier. If it is, that you then say, well, let's not make a prediction, let's fall back. And if it's not an outlier, it might also be good to check if the model certainty, or the proba that's in the model, if that is high enough. And if it isn't, that might also be a nice reason to perform a fallback scenario. Only when these two checks pass, then should we take the action that the original classifier takes. If you want to construct something like this, and you already have an outlier detection model, as well as a classifier, then the function classifier object can also be used to very easily declare systems that do exactly this. To give an example, I have written down the pseudocode that you might need to construct something like this. I'm assuming that you already have your outlier detector, and I'm also assuming that you already have your classifier. But then if you want to construct the diagram that we had before, the only thing you have to do is declare this onMakeDecision function. Inside of this function, the first thing that needs to happen is you first need to have a classifier that makes a prediction on all the data points that are passed in. Next, if there is any doubt, that is to say, we calculate the probability values for each class, and if the maximum of all those probability values is less than a threshold, well, then we are going to not use the predictions that we had. Instead, we are going to override it by saying, well, the class is now doubt fallback. And the numpy where function makes it really convenient to write this logic. We also like to make sure that it's not an outlier, so we apply a similar trick. If we have an outlier detection model that's pre-trained, we can make a prediction, and if the prediction says it's an outlier, then we can assign another label instead of the original predictions. This gives us our make decision function, and our function classifier makes it very easy to then accept that function, and we now have a fallback model that you can use in scikit-learn grid search like you're used to. Now, I hope you agree that designing systems like this is beneficial in practice. It is really nice that we can add our own little logic in front of an existing machine learning model, because that allows us to give it behavior that we are interested in. I also hope it makes it clear that the goal of this package isn't to make rule-based systems that act as if they're just predictors. Instead, we want to construct rule-based systems using pre-existing machine learning models. The idea being here that this gives us a nice balance between natural intelligence and artificial intelligence. Let's consider another way of constructing rule-based systems. And to explain this, I will be using a dataset that is in the Scikit Lego package. Now, to get the data that we're interested in, what we got to do is we got to import this load penguins function. All we can do then is we can call the function like you see here, and this gives us a data frame. The goal of this dataset is to predict the species of penguin based on the properties of the penguin, like the body weight or the length of the flipper. To get a different view of the dataset though, what I'm doing below is I am using this module inside of Human Learn, the experimental interactive module, to generate some interactive charts. And here you can see one of these interactive charts. I'll just zoom out a bit. And the interactive chart that you see here shows these different classes appear for the different kinds of penguins that we have. Now, one reason why people like doing machine learning is because it's kind of hard to come up with a rule-based system that can handle data points like this. Writing an if-else statement that will perfectly describe this area over here is relatively tricky. But what if we could just go ahead and draw it instead? If I'm to consider this dataset over here, I can argue that it's not really that complex. As a human, I can kind of draw the area where I expect the green dots to be in, and I can pretty much eyeball what the algorithm should look like. And that allows me to draw out these polygons. To get started with drawing, I gotta select a color that I'm interested in this case red, which corresponds to this class. And then I can double click and click and click, 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 click. And when I'm done making the polygon, I can double click once more, and then I've got a shape. I can click and drag this shape if I'm interested. And what I can also do is I can use this edit button over here to edit the shape. But the main point I want to make here is that we can also declare rules by drawing them. And this is just one drawing, but let's also make another one. And now I've got these two drawings that, as far as I'm concerned, should serve as a pretty okay classification algorithm. Now, to use this as a classification algorithm, it's useful to point out one more thing. Note that we added a chart to this CLF object over here. And that object is this interactive charts object, the one that took the data frame as input and this species as a label column. What I can do is I can take that object and ask it for all the polygons that I've drawn so far. Using this JSON blob, we can reconstruct the drawings that we made, and we can use a point-in-poly algorithm to check if a new point is in one of these polygons at any given point. And if that's the case, we can make the appropriate classification. To get this to work though, we're going to have to import something called an interactive classifier. The idea behind this classifier is that we can define a scikit-learn compatible model from this JSON blob. And what we can then do is we can generate our X and Y datasets as we would normally from a data frame, and then we could use this model as if it was any scikit-learn model that we're used to. And to emphasize how these classifications work, I've added a little bit of code that makes the matplotlib charts, and you can verify yourself that the plots that you see here do correspond with the drawings made earlier in this notebook. It deserves to be mentioned though that these drawn models have properties that you might not have thought of up front, and some of these properties are actually quite beneficial. What I'm doing now is I'm taking the exact same model as I drew before, but now I'm having it predict a new example over here. And this new example is predicted with a class of Adelie, and we can see that it's doubting between two classes in particular. If I were to scroll up now, then I can also explain why. Compared to this chart, the new example point that I've made is somewhere over here. whereas for the other chart, the same point will be somewhere around here. So that explains why it's having trouble making a proper classification. But let's now say that the data that I'm getting in, it's incomplete. It's missing a value. Well, in this case, if this was the value that's missing, then I could scroll back up to here, and then where before the point was inside of this polygon, it now isn't anymore. So this chart is not giving us any more information for our classification task. However, because these two variables are definitely known, we can definitely still say that the penguin is in this region. And from a machine learning perspective, that means that our drawings are robust against missing data. We now see that we're predicting a new class, and that's because we are now zooming in on these two features and no longer using these two. There is another use case for these drawn machine learning models, so to say. If we have a look at the drawing right here, you'll notice that there's a couple of points that kind of fall outside of the polygon that we drew. And in this particular case, we can perhaps make the argument, maybe some of these points are outliers. Especially if we were to zoom out. I hope you recognize that this machine learning model really only has a comfort zone around here. If we were to see points that are definitely on the outskirts of this comfort zone, then it'd be nice if we can have a system that says, hey, that's an outlier. We should treat those points differently. Luckily for us, what we can do is we can take the same drawing that we use to make a classifier and use it as an outlier detection system. Where before, we would check whether or not a point was inside of a polygon in order to make a decision, the outlier detector will check whether or not the point is outside of polygons. And there's a hyperparameter. We can specify the minimum number of polygons that a point has to be in order for it not to be an outlier. But to give a simple demo of this feature, you'll notice below here that I am using the interactive outlier detector as opposed to the classifier, and then I'm following very similar steps as before. But the main thing that you'll notice now is that when I make the chart of the predictions, that all the points on the outskirts are indeed now classified as an outlier. And again, what we could do is we can make changes to this drawing over here, and then we would get different results. In all the drawings that we've made so far, we've had the luxury of this label that was available. However, you can also imagine situations where we don't have a label readily available, and in these situations it might be nice to use this drawing mechanic to actually assign labels to data points. So as a demo, let's just add group 1 and group 2 as labels here. Because the labels parameter here is now a list, these interactive charts will no longer internally check for a column, and instead it will assume that these are the values that you want to assign. So if I now were to run this, you'll notice that the colors in the chart here are gone. I do, however, still have the ability to make a drawing like before. And I can use this drawing to make an outlier detector or a classifier, but what I can also do is use this drawing in a pre-processing step. Human Learn comes with this interactive pre-processor, and just like in the examples before, it is able to read in this chart data, but instead of acting as a predictor, it can act as either a scikit-learn transformer, but it can also be used in a pandas pipeline, as you see below here. In the case of pandas, what will happen is it will add 2 new columns with counts, how often a data point was in a polygon. And if I were to use the scikit-learn flow instead, I would get the same counts, but as a NumPy array. Now, this interactive charts API is relatively experimental. Currently, it only allows for 2D charts, but you can imagine that other visuals will also be added in the future. Things like histograms can also be used to make selections. The main utility of this library, though, is to maybe start thinking a little bit differently about machine learning models, and to maybe start thinking about rule-based systems instead. The goal isn't to throw machine learning out the window, but instead to use machine learning algorithms with some business rules around them, such that literally machine learning models can play by the rules.
I hope you enjoyed watching these videos on Scikit-learn. It's a vast ecosystem, and we've only really been able to scratch the surface here, but I hope that I've been able to explain enough for you to either get started or to explore the tool more. If you enjoyed these videos, then I would like to mention that there is some other machine learning content out there that you might also appreciate. In particular, I make a lot of videos on the Calm Code website, so definitely feel free to check that out. Also, if you're interested in learning more about natural language processing, then you might also appreciate the videos I've been making on the official Spacey channel. In this series of videos, I'm trying to make a model that can detect programming languages. And if that sounds interesting, definitely feel free to check that out as well. And if you're interested in learning more about natural language processing, definitely feel free to check out the Algorithm Whiteboard channel on YouTube. It's a playlist that I maintain on behalf of my employer, Raza, and you'll find many examples and explanations of algorithms there as well. If your interest is to learn more about scikit-learn though, then I might also have some other recommendations for you. For starters, definitely feel free to check out Free Code Camp. I've been in industry for over 7 years, but I still find many useful courses and hints on a wide variety of topics on this website, which includes related toolkits like NumPy and Pandas. Second, I might also recommend checking out the PyData YouTube channel. Understanding how scikit-learn works is great, but sometimes you would also like to hear anecdotes and lessons learned from applying scikit-learn in practice. And the PyData channel on YouTube is a great resource for just that. Now, the third and final resource that I really recommend is the scikit-learn documentation page. Scikit-learn is a gigantic library, and there's a lot of features that to this day I still discover basically just by reading the documentation. But there's also something specific about the documentation that I would like to highlight. If you go to the documentation page, you'll find a couple of subsections. There is a user guide that you can follow, but there's also a subsection over here under More where it reads Related Packages. You see, scikit-learn isn't just a package. At this stage, you could also say it's an ecosystem, and there are many different projects for specific use cases that might seriously help out. There's experimentation frameworks, tools for model selection. There's also extra support for tools that have to do with time series. And although the list of tools here can be intimidatingly large, I really do recommend just having a look here simply to get a feel of what you could do with scikit-learn. So I hope you'll give this documentation page a glance. And once more, I hope that you'll be able to use scikit-learn to do meaningful work with machine learning. Thanks for listening.